Hello friends, welcome back to week number 3 of our course on fundamentals of conduction and radiation. And this week we are going to talk about the one dimensional steady state heat conduction situations. In the previous week we have developed the basic heat diffusion equation corresponding to all the 3 coordinate systems, the Cartesian, cylindrical and spherical coordinate systems. And now each of them has their own domain of applications, and the complete form of equations which you developed, that of course has its own applicability. Before proceeding further, let us just summarize the equations that I derived in the previous week. If I write first in the Cartesian or rectangular coordinate system, so in the Cartesian coordinate system our basic heat diffusion equation was of the form dou dou x of k x dou t dou x plus dou dou y of k y dou t dou y plus dou dou z of k z dou t dou z plus q 0 triple prime is equal to rho c dou t dou t, where k x, k y and k z refers to the thermal conductivity in all the 3 coordinate direction, and q 0 triple prime is the volumetric rate of energy generation or rate of heat generation inside the system per unit volume, and the term on the right hand side is the transient term which refers to the time rate of change of energy content of the system. If we write the same thing in cylindrical coordinate system, then you will be getting the one that we have developed as 1 upon r dou dou r of r k r dou t dou r plus 1 upon r square dou dou phi of k phi dou t dou phi plus dou dou z of k z dou t dou z plus the final two terms remains the same, q 0 triple prime is equal to rho c dou t dou t. While in Cartesian coordinate system our coordinate directions are x, y and z, in cylindrical coordinate system it is r which is radius, then the azimuthal angle phi, and of course the axial direction z. And accordingly we have written this equation, k r, k phi and k z refers to again the thermal conductivity in the 3 directions, and then we have the general form of the equation. And finally, in the spherical coordinate system, where our coordinate directions are r, theta and phi, along with radius we have both the polar and azimuthal angles, then it becomes 1 upon r square dou dou r of r square k r dou t dou r plus 1 upon r square sin square theta, sorry, r square sin theta. Let us write the theta part first, dou dou theta of k theta sin theta dou t dou theta plus 1 upon r square sin square theta dou dou phi of k phi dou t dou phi plus the conventional volumetric rate of heat generation equal to the time rate of change of energy content of the system. Now, these are the 3 equations that we have developed in the last week, but we have not talked about their applications, or we have not solved them to simulate any real life situation. Because the equations, these 3 form of the equations, all of them are very complicated. Firstly, they are partial differential equations. Secondly, you can see them, they are dependent on both space and time. So, there are 4 independent variables, one is time and then the 3 space coordinates. Then we have the direction dependence of thermal conductivity, we have the volumetric energy generation, and overall it is a very complicated situation, and solving them is definitely very complicated. Thankfully, in several real life situations, in several engineering applications, we can visualize the system to be something like having a one dimensional heat transfer. One dimensional heat transfer refers while practically all systems are 3-dimensional in nature, but 1-dimensional refers the rate of heat transmission in one direction is significantly larger than the rate of heat transmission in the other two direction. Like if I talk about the Cartesian one, then from the general equation we know that there are 3 heat conduction we can get. Like in the x direction it can be written as minus kx dou t dou x, in the y direction it is minus ky dou t dou y, and in the z direction it is minus kz dou t dou z. Now, these are the 3 components of the power transmission or heat conduction in the 3 direction you can say. Now, if the situation is that your q dot x is way greater than q dot y and q dot z, then it is very logical that we can neglect the second two terms. We can neglect any heat conduction in the y and z direction and consider only the heat conduction in the x direction. And if that is the scenario, in that case this particular equation can be written as dou dou x of kx dou t dou x plus the next two terms goes to 0, or we are neglecting them because corresponding heat conductions are negligible compared to the heat conduction in x direction, plus qg dot triple prime is equal to rho c dou t dou t. And if we are talking about an even simpler case, that is we are talking about steady state, means of course this one we can write when heat conduction in the x direction is significantly larger than heat conduction in the y and z direction. And along with that, if we assume it to be steady state, then what we mean by steady state? There is no variation in time is equal to 0. That means any dou dou t quantity can be said to be equal to 0. In that case, your equation becomes even simpler. Now, see in the first line, when we have written the generalized diffusion equation in Cartesian coordinate, we had 4 independent variables x, y, z and also time. Now, as we have neglected the variation in y and z directions, then there is only 2 independent variables in the second equation, x and t. And now, once we are going for steady state, the time is also not there, then we are left with only a single independent variable which is x, and accordingly this equation, which is a partial differential equation, gets converted to an ordinary differential equation of the form d dx of k dt dx plus qg dot triple prime is equal to 0. This is when we are talking about a steady state situation. Here we have dropped the subscript x in the definition of k, because ky and kz are not coming into picture. We have to bother about heat conduction only in the x direction, and therefore kx is the only one that is of our importance. If k is independent of space coordinate, that becomes even simpler, but we do not need to go into that situation for the moment. Now, the question is, in what kind of scenario we can go for such kind of approximation. There are several cases, like as I have mentioned, heat conduction in y and z directions are negligible compared to that in the x direction. Now, that is possible when the temperature gradient is 0. Now, in what kind of situation temperature gradient is 0? Let us say we talk about q dot y. For this q dot y to be equal to 0, we need to have this ky dou t dou y to be equal to 0. Now, ky is a property, that is thermal conductivity, so it can't be 0. Then in that situation we must have this temperature gradient in the y direction to be tending to 0. Now, when that is possible, one possibility is there is an uniform temperature field acting in the y direction. Other possibility is the y itself, or the length scale in the y direction itself, is extremely large. The length scale in the y direction is extremely large compared to the length scale in the x direction. Then this is also possible. Like if we are talking about a system having length of Lx in the x direction, Ly in the y direction and Lz in the z direction, and if suppose Ly and Lz both are very large compared to Lx, then we can virtually write that any dou dou y quantity and dou dou z quantity will be extremely small compared to any gradient in the x direction, because the length, because of the difference in the length scale, and that is the most common situation where we can neglect any variation particularly temperature in this case in the y and z direction. So, the temperature gradient in the x direction becomes the only important one to us, and accordingly heat conduction in the x direction is the one that we have to consider in detail. A very common example, just look into the wall of the room where you are sitting. Just think about the wall. Commonly your wall may be having a height of 3 meter, may be having a width of 3 meter, 5 meter, 10 meter, depending upon where you are sitting. Like common houses can easily have a 3 meter by 3 meter walls, and if you are sitting in a brick classroom, then the length can be even larger. 8 to 10 meters can easily be the length of the wall on one side, and similarly the height is 3 meter or something like that. But what about the width? What about the thickness of the wall? The thickness of the wall can be something like say 25 centimeter, 50 centimeter. That is, we are talking about a dimension of Ly. Say your in the y direction your length is 5 meter, in the z direction, that is in the vertical direction, your length is 3 meter, whereas in the x direction your length is say 50 centimeter, that is 0.5 meter, which is significantly smaller compared to the other two. And 50 centimeter is also quite thick walls that we are talking about. Common household walls may be even thinner than this, something like 25 centimeter or even lighter. And in that case, therefore, the length scale in the x direction is substantially smaller compared to the length scale in the y and z direction. Accordingly, we can say for this kind of scenario, the gradient in the x direction has to be much larger than the gradient in the y and z direction, and therefore, heat conduction through your building wall can easily be treated as a one dimensional problem. Similarly, several other examples also we shall be seeing as we shall be solving numerical problems later on, and you also be getting several scenarios in your books. So, if we erase this, just look about the cylindrical coordinate system. The general equation that we have, suppose we are talking about a situation where heat transmission in the radial direction is the only one of importance. Like just think about a common scenario, we are having a cylindrical rod, just a common rod or a pipe which is having a length of something like 10 meter, but its diameter is something like say 10 centimeter. Then we are having 10 meter on one side and 0.1 meter on the other side, and definitely the gradient in the r direction, the radial direction, has to be significantly larger than the gradient in the z direction. And quite often we neglect the phi variation also, because I have probably have mentioned the term, we call it axisymmetric, that is the variation in the phi direction can be neglected. So, in that scenario, the one dimensional unsteady form of the heat diffusion equation in cylindrical coordinate becomes 1 upon r to dou r of r k dou t dou r. Again I am dropping the subscript in the expression for k, because I am talking about conduction only in the r direction, plus q g dot triple prime is equal to rho c dou t dou t. This is possible when the heat conduction in the r direction is significantly larger than the heat conduction in the phi and z direction. And if we are further talking about a steady state situation, then we can convert this onto an ordinary differential equation, which is of the form 1 by r d d r of r k dt dr plus q 0 triple prime is equal to 0. This is possible when we are talking about a steady state situation, that is any variation or gradient in time with time can be neglected. Similarly, in the spherical coordinate system, again if we neglect the variation in the phi and theta direction, just consider a ball, a solid sphere maybe. In that case, quite often the variation in the phi and theta direction may be neglected, and the major variation that you get is only in the radial direction. So, if I directly write the expression for spherical coordinate system, heat conduction only in the radial direction and under steady state, then this equation becomes 1 by r square d d r of r square k dt dr plus q 0 triple prime is equal to 0. This is when your q dot r is significantly greater than heat conduction in the phi and theta direction, and any time variation can be neglected. And in this particular chapter, in this module, we shall be talking primarily about this one dimensional steady state form of the heat conduction equation, because they are extremely important in several engineering applications, and secondly they are very easy to analyze, they are very easy to model mathematically. Of course, you can see that the partial differential equation has now got converted to an ordinary differential equation, so it can be solved very easily. Secondly, there is an alternate approach where we shall be using the concept of thermal resistance, where we do not need to go for the solution also, we can do it in even easier way. So, let us start with the Cartesian coordinate system. Okay, another point I am mentioning here, the Qg triple prime, Qg dot triple prime, the volumetric heat generation rate I have written in all the three equations, that is the one dimensional steady state heat conduction equation in Cartesian coordinate, which is this, one dimensional steady state heat conduction equation in cylindrical coordinate, which is this, and one dimensional steady state heat conduction equation in spherical coordinate, which is this. I have written this one here, the volumetric heat generation rate, but I am not going to consider this one for this week's lecture, that is this Qg dot triple prime also will be set to 0 for the moment. Next week I shall be including this one back and doing further analysis for that. So, we are going to start with heat conduction in plane wall. Plane wall is synonymous to the Cartesian coordinate system, and we are talking it as plane wall because the wall, building wall, is the most simpler example or straightforward example of a 1D heat conduction in Cartesian coordinate. So, look at the situation what is given. We are talking about a wall. Let us say this is your x equal to 0, this is x equal to L. So, the thickness of the wall is L. Let us say the area of each of the faces of the wall is equal to A. One side of the wall is kept at temperature Ts1, other side is kept at the temperature Ts2, and fluid, air or some other kind of fluid is flowing on both the surfaces. One side you are having a hot fluid flowing with temperature T infinity 1, and other side it is flowing with a temperature T infinity 2. For T infinity 1 is greater than T infinity 2. So, it is given that the hot fluid side temperature T infinity 1 is greater than cold fluid side temperature T infinity 2. So, you can expect the heat to get transferred from the hot fluid to the left face of the wall, let us say the face number 1, then via, and what should be the mode of heat transfer from the hot fluid to the phase 1 of the wall? That has to be convection, because we are talking about a flowing fluid over a solid surface. So, via convection heat gets transferred from the hot fluid to the phase 1 of this, then 1 to phase 2 via conduction, because it is a solid wall, and then from phase 2 to the cold fluid which is maintained at temperature T infinity 2 via convection again. Corresponding convective heat transfer coefficients are given as H1 and H2. But before taking into account the heat convection with hot and cold fluids, let us just stick to the conduction part. Ts1 and Ts2 are the temperatures of the two faces of the wall. So, using our common sense, we can say that as heat always gets transferred from high temperature to low temperature. So, T infinity 1 has to be greater than surface temperature for phase 1 Ts1, which has to be greater than Ts2, and that has to be greater than T infinity 2. So, from this to this, the mode of heat transmission is convection. Similarly, from this to this, the mode of heat transmission is again convection. The second one is characterized by heat transfer coefficient of H2, this is characterized by a heat transfer coefficient of H1. However, our first interest is this one Ts1 to Ts2, which is done by conduction. So, we have considered A to be the area of the wall, and we are considering a thermal conductivity say K in this x direction. I am not putting any subscript x because we are talking again about 1D heat conduction. So, what is the condition here? Then what are the conditions that we are imposing? Firstly, 1D heat conduction, secondly steady state. So, considering this, we have already developed the equation. Then I am putting a third condition which I verbally mentioned, there is no heat generation and fourth, we are considering the thermal conductivity to be constant, which refers that K is not a function of x. That is an additional constraint that I am putting in. So, what was the equation that I developed in the previous slide? That was d dx of K dt dx plus q 0 triple prime is equal to 0. There is no heat generation, that means q 0 triple prime is equal to 0. So, we have now d dx of K dt dx is equal to 0. So, we have to integrate this equation with respect to x to get the solution. Then what we have, d of K dt dx integration this, that gives us. So, we have to integrate this one equal to 0. Getting this, we are getting K dt dx is equal to some constant C1, and as we are considering K to be a constant, then let us say first constant is C1 prime, and then we are taking the K on the other side, C1 prime upon K, which become C1. So, dt equal to C1 dx, again we are integrating this. So, we get T as a function of x is equal to C1 x plus C2, a very straightforward linear form of equation, that is temperature variation within the body in the x direction will be linear, and exact nature of the profile will be dependent upon these two constants C1 and C2. So, to identify these two constants of integration C1 and C2. Now, how to identify that? We are given with the temperature Ts1 and Ts2. So, let us make use of them. At x equal to 0, it is given that T is equal to Ts1. So, if I put this one, then Ts1 is equal to C2. Similarly, at x equal to L, temperature of the wall is equal to Ts2. So, we have Ts2 equal to C1L plus C2. Now, just we have got C2 is equal to Ts1, that is C1 now becomes Ts2 minus Ts1 upon L, or as we know that Ts1 is higher than Ts2. So, it is better that we write this one as minus of Ts1 minus Ts2 upon L. So, what becomes our temperature profile then? T at x is equal to C1 x plus C2. So, C1 is minus of Ts1 minus Ts2 upon L into x plus C2 is Ts1, and there are several ways this one can be rearranged, but probably it is better to express this one as Ts1 minus Ts2 into x upon L. So, this is the temperature profile that we are getting through this wall, and once we know the two end temperatures Ts1 and Ts2, then we shall easily be able to calculate this one. And if our interest is to know the heat transmission rate, of course, we have got from here that is a linear profile, that is exactly shown here. It is a straight line joining Ts1 and Ts2. Now, if our interest is to know the heat transmission rate, the rate of conduction heat transfer, that also we can easily calculate. Say if we want to calculate the rate of heat transfer, then we know that q dot in the x direction following conduction only will be equal to minus k dt dx, that is equal to differentiating this Tx with respect to x, then we are having this as minus k of C1, that is equal to, putting the expression for C1, Ts1 minus Ts2 into K upon L. This is the heat flux, and finally, if we want to have the total heat conduction, then that is equal to heat flux into the area, that is K A by L into T S 1 minus T S 2. Let us proceed with this. So, we have just developed that the temperature profile inside your solid has become T S 1 minus T S 1 minus T S 2 into x upon L, and the conduction heat transmission in the x direction we have got to be equal to K A upon L into T S 1 minus T S 2. If we rearrange this second equation a bit and write this one as T S 1 minus T S 2 upon q dot x, then we can write this one to be equal to L upon K A. Now, how this particular form is looking like? This left hand side, on the numerator what we have? On the numerator we have the temperature difference, in the denominator we have the conduction heat transmission rate or conduction heat transfer rate. Then how the numerator is looking like? That is the potential difference because of which the heat transfer is taking place. What about the denominator? Denominator is the result of this potential difference. And then how this form is looking like? In the first week itself we have introduced the concept of thermal resistance. So, can you relate this one to this? On the left hand side we have the potential difference on the numerator and the effect of that in the denominator, and we can easily relate this to the Ohm's law of heat transmission, Ohm's law of electricity, where we can easily write, suppose if E1 minus E2 refers to a potential difference between two locations 1 and 2, then corresponding result will be equal to current I into R, or I upon E1 minus E2 upon I will be equal to R, where R is the resistance. Just similarly, whatever we are getting there, this is also called the conduction resistance. L upon K A, of course, only in the Cartesian coordinate system, where L is the length scale associated with this conduction heat transfer, there is the thickness of this particular block, K is the thermal conductivity, and A is the area of this that is perpendicular to the plane of this screen. So, this area is A, this area basically is, we are talking about something perpendicular to the screen, that is L upon K A, and this is the conduction resistance. So, we can virtually think about using an electrical analogy, that on one side of the wall you are having a potential T S 1, on the other side you are having a potential T S 2, and in between you are having a thermal resistance of L upon K A, and accordingly some heat transmission Q dot X will be happening between T S 1 and T S 2. And just like shown here, then we can easily draw an electrical circuit where this side you have the potential as T S 1, this side you have the potential as T S 2, and in between you have this conduction resistance, which we have just got as L upon K A in Cartesian system, and accordingly we can get the value of Q dot X. So, once we know that these two temperatures and we have the information about the thermal conductivity and dimensions of the wall, you can directly calculate the heat transmission, that is Q dot X, without directly solving the ordinary differential equation. But now quite often the situation is that we do not know directly the value of T S 1 and T S 2, rather our information available is the about hot fluid and the cold fluid. That is, we know the hot fluid temperature T infinity 1, we know the cold fluid temperature T infinity 2, and we also know their heat transfer coefficients H 1 and H 2, but we do not know T S 1 and T S 2. Then somehow we have to estimate the value of T S 1 and T S 2, and then only we can go for this electrical analogy to get the value of Q dot X. Then how can we estimate T S 1 and T S 2? So, first we talk about the left hand side. So, at this particular juncture, on this side your mode of heat transfer is convection, on this side your mode of heat transfer is conduction, and as we are talking about only one dimensional heat conduction, then entire energy transmission direction is this one only. So, heat is getting transmitted only in this direction. Now, as the system is under steady state, there is no temperature variation with respect to time at a particular location. That indicates that the system has to be in some kind of balance and the wall is not having any net energy storage. Also, there is no heat generation inside the wall. Then, to maintain this energy balance, it has to be satisfied that the rate of convective heat transfer in this from the hot fluid to the wall in this direction, the amount of energy transmitted by the hot fluid to the wall by convection in this direction, that has to be balanced by the amount of energy conducted from the wall to the interior of the wall, or from this particular face of the wall to the interior, so that the temperature remains constant with respect to time. This is just the convective boundary condition, nothing else. So, let us apply the convective boundary condition on the hot fluid side. Then the amount of conduction is happening is minus K dt dx. Okay, let me write the area also, minus K A dt dx at x equal to 0. That is the conduction happening on the interior side, and on the exterior side of the face what is happening? It is heat transfer by convection. So, corresponding heat transfer coefficient H1, using Newton's law of cooling we can write it is H1 into again the same area we are talking about, into the temperature difference, which in this case is T infinity 1 minus T s 1. Now, what is dt dx? In the previous slide we have seen that dt dx in this particular case is nothing but C1. So, minus K A into dt dx at x equal to 0, which is C1, that is minus T s 1 minus T s 2 upon L, minus of T s 1 minus T s 2 upon L at x equal to 0, but it is redundant to write x equal to 0 because there is this gradient is constant, it is independent of x, that is equal to H 1 into A T infinity 1 minus T s 1. So, we can now solve this, we can rearrange this entire equation. So, we have K A upon L into T s 1 minus T s 2 equal to H 1 A into T infinity 1 minus T s 1. Similarly, if we write the energy balance, similarly convective boundary condition we are applying at x equal to L, then what we can write? Minus K A dt dx at x equal to L is equal to, now corresponding convective heat transfer rate will be H 2 into area into T s 2 minus T infinity 2, that is minus K A into temperature gradient is T s 1 minus T s 2 upon L at x equal to L is equal to H 2 A T s 2 minus T infinity 2, or just arranging the same way, we have K A upon L into T s 1 minus T s 2 is equal to H 2 into A into T s 2 minus T infinity 2. So, now we have got two equations, and this is say our equation number 1, this is our equation number 2. Once we have idea about the information say H 1, H 2, K, A, L, and also T infinity 1 and T infinity 2, then we can solve these equations to get T s 1 and T s 2 from this. But is there at all any need to go for such complicated expressions? Look at this, both your equation 1 and equation 2 are having the same term on the left hand side, and what is this term? If I go back, this term, okay, it was there in this slide itself. This slide term is this one only, that is the rate of heat conduction, which is also logical, because whatever amount of heat that gets transmitted from the hot fluid, the same amount of heat under steady state will be flowing to the other wall, other face of the wall, and then the same amount of heat will be passing on to the cold fluid, that is this q dot x remains the same as we are talking about a simple 1D heat conduction and also under steady state. That means, we can write this rate of heat transmission q dot x on the hot fluid side, this is equal to, by convection, this is equal to H 1 into area into T infinity 1 minus T s 1. Then interior to the body, interior to the solid block, you have K A upon L into T s 1 minus T s 2, and again on the cold fluid side it is equal to H 2 into A into T s 2 minus T infinity 2. Now, if we rearrange all of them again, we know that q dot x can be written this way. Now, for the hot fluid side, we have q dot x is equal to H 1 into A into T infinity 1 minus T s 1, or if we just write the way we got the conduction resistance, it will be equal to T infinity 1 minus T s 1 upon q dot x will be equal to what? Will be equal to 1 by H A. Now, what is this bracketed term? This is the temperature difference required for the convective heat transfer. The denominator is the result of this potential difference. Then this is nothing but your convective resistance on the hot fluid side. Similarly, on the cold fluid side, if we write q dot x is equal to H 2 into A into T s 2 minus T infinity 2. That is, if we rearrange the same way, T s 2 minus T infinity 2 upon q dot x is equal to 1 by H 2 A. I forgot to forget the subscript here, it should be H 1. So, again in this case, this is your convective resistance on the cold fluid side, and in between we have the conduction resistance also, which you have got here. Then how we can visualize the system? I have already the diagram shown here, but still I am writing this step by step. So, to start with, we have a potential energy source maintained at temperature T infinity 1. Then via convection, it is transmitting energy to another node maintained at temperature T s 1, and this heat transfer is happening through a resistance, a convective resistance, which is 1 by H 1 into A, and q dot x amount of heat is getting transmitted. So, once this heat reaches T s 1, then this is getting transmitted through a conduction resistance to another node maintained at T s 2, and this conduction node is having a resistance which we have got here as L by K A, and then from this T s 2, again via convection, energy is getting transmitted to the low temperature side, which is maintained at T infinity 2, and this heat transfer is getting facilitated to another convective heat transfer resistance, that is 1 upon H 2 A. Then if we just want to have a direct relationship between heat transmission from T infinity 1 to T infinity 2, then how we can do this? Just neglect the intermediate temperatures. Then we can directly think about that q dot x amount of heat is getting transmitted from T infinity 1 to T infinity 2, and that is happening through 3 different resistances. That is, we can write now a generalized expression of T infinity 1 minus T infinity 2 upon the q dot x. Now, T infinity 1 minus T infinity 2 is the overall potential, the overall temperature difference because of which this heat transfer is happening, and that heat transfer is q dot x only. Then this should be equal to, this is using our electrical analogy, this should, we can visualize that there are 3 resistances, 2 convective resistances and 1 conduction resistance in between, and these resistances are connected in series here. This because the same heat transmission rate is applicable for all of them, but the temperature difference across each of them, that is different. That is, the heat transmission rate is same for all of them, but the potential difference across each of them is different. Therefore, we can say that they are connected in series, very similar to the electrical systems. And now, when we are having several resistances connected in series, how we get the equivalent resistance? We just add them up. So, just the same thing we can do here. We can say this should be equal to some R equivalent, and this R equivalent is your R convection on the hot fluid side plus R conduction plus R convection on the cold fluid side, that is on the hot fluid side the convective heat transfer resistance, convective thermal resistance is 1 upon H A, conduction resistance is L upon K A plus the final convective resistance is 1 upon H 2 A. So, once we know each of the individual resistances, we can easily get their equivalent resistance, and we can directly calculate the value of Q dot X without needing to know the values of T S 1 and T S 2. We just need to know the two end temperatures and all the resistances, then this T S 1 and T S 2 are never coming into picture. We can directly get the value of Q dot X using only the two end temperatures. Now, if once we know the value of Q dot X, then if we want to calculate the value of T S 1, how can we do this? So, just consider the first convection part. In that case, like we wrote earlier, T infinity 1 minus T S 1 upon Q dot X will be equal to the corresponding convective resistance or convective resistance on the hot fluid side, that is 1 upon H 1 into A, and hence we can separate out the terms from here. T infinity 1 minus T S 1 is equal to Q dot X upon H 1 into area, or T S 1 is equal to T infinity 1 minus Q dot X upon H 1 into area. Similarly, if we want to calculate T S 2, then we can do that using the convective heat transfer on the cold fluid side. For that case, we can write T S 2 minus T infinity 2 upon Q dot X is the convective thermal resistance on the cold fluid side, that is equal to 1 by H 2 A. So, T S 2 minus T infinity 2 is equal to Q dot X upon H 2 A, and then T S 2 is equal to T infinity 2 plus Q dot X upon H 2 A. So, we do not need to know the values of the two phases T S 1 and T S 2 to get the Q dot X, rather using the value of Q dot X we are getting their values later on. So, this way any one dimensional steady state heat conduction scenario, at least in Cartesian coordinate, can easily be reduced to such kind of series of conduction and convection resistances. Just look at this, something known as a composite wall. Here instead of one, there are 3 layers of solids inside the wall. Then we can think each of them are having different thermal conductivities. So, we can think about there are 3 different conduction resistances acting in series with each other. Look at the first part, the block A of the solid. The temperature is T S 1 at one side and T 2 on the other side. Then if we consider that Q dot X is the amount of heat transmission that is taking place by conduction, it is 1D and steady state. Please remember that whatever we are discussing, that is applicable only for one dimensional steady state heat conduction. So, if Q dot X is the amount of heat conduction, then for block A we can directly write using the concept of thermal resistance. Okay, let us start from the hot fluid side. So, if we write for hot fluid side, then we can write the temperature difference T infinity 1 minus T S 1 divided by Q dot X will be equal to 1 upon H 1 into area. Let us say A refers to the area of this wall. Then the first layer, the layer number A, it is subjected to conduction. So, temperature is T S 1 on one side and T 2 on the other side divided by Q dot X is equal to L A upon K A, which is this resistance. Then layer B, prevailing temperature difference is T2 minus T3 upon Q dot x, that should be equal to LB upon KB into area, which refers to this second resistance. Then we have the third layer, layer C. It is having temperature T3 on one side and Ts4 on the other side, and Q dot x. So, that should be equal to LC upon Kc into area. So, this is this third conduction resistance we have, and finally, on the cold fluid side we are having convection. So, here the temperature difference is Ts4 minus T infinity 4 upon Q dot x is equal to 1 upon H4 into area. And if we want to write in overall sense, then we can directly write that R equivalent is equal to the summation of all the 5 resistances, that is the first convective resistance 1 upon H A, then conductive resistance corresponding to the first layer L A upon K A into A, plus corresponding to the second layer L B upon K B into A, plus the third layer L C upon K C into A, plus the final convection 1 upon H 4, it is there, okay, 1 upon H 4 into area. And then using that idea we can directly write the overall temperature difference. We have T infinity 1 on one side and T infinity 4 on the other side, and Q dot x is the rate of heat transfer, that should be equal to R equivalent. Then from the knowledge of these two fluid temperatures T infinity 1 and T infinity 4, and from each of these resistances you can calculate the value of Q dot x, and then using Q dot x you can easily calculate all these intermediate temperatures Ts1, Ts4, T2, T3 etc. They all can be calculated. So, this way we can connect several resistances in series and we can do the analysis very easily without bothering about the need to solve any ordinary differential equation even. But I keep on repeating, there are several assumptions that we are considering. The assumptions which I wrote earlier, I am just repeating it here again. This is applicable strictly for one dimensional heat conduction, and under steady state no heat generation, and the thermal conductivity is also a constant. It is not a function of that only single space coordinate that we are considering. Only when all these 4 conditions are satisfied, then only we can go for such kind of thermal resistance concept, and we can easily form resistance circuits using the electrical analogy. So, this is just the one that I talked about earlier. So, in this case, as I have written, T infinity 1 minus T infinity 4 upon Q dot x is equal to that R equivalent, the equivalent resistance for this circuit. Quite often instead of writing this way, we write in another alternate form, just somewhat to be consistent with the Newton's law of cooling. In case of convection, how we represent Q dot convection, you know, we always write as some heat transfer, convective heat transfer coefficient H into area into that delta T. We have seen how we can represent the radiation also following this form. For conduction, we generally do not go for a form like this, but when we are talking about such an equivalent circuit, occasionally we would like to have a form somewhat analogous to this particular form of Newton's law of cooling. So, if we write now as the Q dot x is equal to T infinity 1 minus T infinity 4 by R equivalent. Remember what we are trying to do here, that is applicable only for this combination of resistances, the total circuit, not on individual resistances, because for individual cases the mode can be conduction or convection, we can analyze them separately, but only for the overall circuit we are trying to identify this. So, this the numerator T infinity 1 minus T infinity 4 can be represented as delta T, the overall temperature difference applicable for this heat transfer, by R equivalent, and if we compare this one with the Newton's law of cooling, then we can write this one as something like U into A into delta T, and where this U A is nothing but the reciprocal of this R equivalent, and this U is known as overall heat transfer coefficient. Just what I was talking about, when we are talking about a series of resistances, then R equivalent can be written as 1 upon U A, or this U A can be written as 1 upon R equivalent. U is the overall heat transfer coefficient, and A is the area at which this heat transfer coefficient is defined. As long as we are dealing with a planar area like this, it does not matter the choice of the area does not matter, because all the areas are, all the surfaces are having the same area. But as we shall be moving to the cylindrical and spherical systems in the next class, then you will see that the area can keep on changing with the change in radius, and therefore, the value of U that you are defining, that depends upon the choice of the area, while the UA product remains the same, but the value of U can vary depending upon the magnitude of the area itself. Now, before I complete here, what is the expression, sorry, what is the dimension of this U? Okay, before going to the dimension of U, let us try to get the dimensions of this R, the thermal resistance. What will be the dimensions of R? We know R is equal to delta T upon Q dot. So, from there can we form delta T is Kelvin, and what about Q dot? That is the heat transfer rate, which is watt. So, that is joule second. So, it is joule into second. So, we can easily write in this form, or generally go for Kelvin per watt. That is the expression for R, or sorry, the dimension for this thermal resistance. You can easily form it from the others also, like say for our conduction, we know that it is L upon K A. If we try to form it from there, L is a length scale, so it is meter. K is thermal conductivity. What is the unit of thermal conductivity? We have developed this earlier. So, that is watt per meter Kelvin, and A is area, which is meter square. So, equivalent from there we are getting Kelvin per watt. And if we try to do the same using the convective transfer thermal resistance, 1 upon H A. So, H you know has the unit of watt per meter square Kelvin, and area is meter square. So, we are getting it to be Kelvin per watt. So, thermal resistance has an unit of Kelvin per watt in SI scale, or you can say temperature divided by heat flux as the dimension. Then what about this U? So, U A is equal to 1 upon R equivalent, or U is equal to 1 by A into R equivalent. So, from there if we try to form the dimension, R equivalent or R has a resistance of, sorry, dimensions of Kelvin per watt. So, it is R is having Kelvin per watt, and A is area, that is meter square. So, it will be watt per meter square Kelvin, just very similar to the unit of the convective heat transfer coefficient, and that should be also, because the idea of this overall heat transfer coefficient comes only from the Newton's law of cooling, and therefore, this U is nothing but an analogous form of that small h in for overall circuit representation. So, its dimension is watt per meter square Kelvin. And also one thing that I would like to mention here, occasionally, though we do not go that route, but sometimes this R, the R that we are representing as delta T upon Q dot, occasionally instead of Q dot we can also represent this one as Q dot double prime, heat flux. In that case, the unit of R will be equal to Kelvin meter square per watt. because heat flux is having a unit of watt per meter square. But this is something that we shall not be doing, but in certain cases, and therefore, to separate them out, occasionally we also put an R double prime to indicate that here the thermal resistance is defined in terms of heat flux. So, I repeat again, R, the thermal resistance, generally put an RTH occasionally, or R convection or conduction, etc. So, this thermal resistance is defined as delta T upon heat transfer rate and having a unit of Kelvin per watt, but sometimes this it is defined in terms of heat flux, then we shall be using double primes and it will be delta T upon Q dot double prime. In that case, the unit will be equal to Kelvin meter square upon watt. So, this is about the overall heat transfer coefficient and the concept of thermal resistance and their combination. But we have so far seen how to connect the resistances in series, but it is also possible to connect them in parallel, just like shown here. The parallel refers to, like in series connection, we have seen that the heat transmission rate through all the resistances will be equal, but the effective temperature difference is different. Whereas in case of parallel, the temperature difference has to be the same, but the heat transmission rate will be different, just like shown here. You can think about, it is an wall having 3 layers. This is your layer E, which is having a thickness of Le and conductivity of Ke. Now, in the third layer, the layer H is having a thickness of Lh and thermal conductivity of Kh, but the intermediate layer that has been broken into 2 parts, like you may have seen sometimes we are having walls, say in laboratories or etc., where some lower part is made of concrete or made of some other material and the upper part is made of glass. It is something similar to this. Here the lower part and upper part are made of different materials. So, the lower part till G having a thickness of conductivity of Kg, and this is having the layer F is having a conductivity of Kf. The lengths are equal, but their areas are different. While the overall area is this A, let us say this area we mentioned about say A2, and this area we take as A1, such that A is equal to A1 plus A2. The temperatures are given as T1 and T2 at the two extremes. Let us say here the temperature is Ta and here the temperature is Tb. Then for the layer E, how we can write the corresponding conduction resistance? In that case, the effective temperature difference is T1 minus Ta upon corresponding heat transmission, conduction heat transfer Q dot x will be equal to Le by Ke into overall area. This is for your layer E. Similarly, the last layer, layer H, effective temperature difference is Tb minus T2 and same conduction heat transmission is happening, and here the resistance can be calculated as L upon Lh upon Kh into area. But the intermediate portion, here the Q dot x now gets divided into 2 parts, one part flows through this F, other part flows through this G. So, if the Q dot x which is coming here, that gets divided into 2 parts, let us say this is Q dot 2 and this is Q dot 1, such that this Q dot x is equal to Q dot 1 plus Q dot 2. Then for the layer F, what we have, the effective temperature difference is Ta minus Tb, and the heat transmission is Q dot 1, corresponding resistance will be equal to its length Lf upon Kf into area A1. Similarly, for the one G, temperature difference remains the same Ta minus Tb, but heat transmission is different, which is Q dot 2, that is equal to Lg, which is same as Lf by Kg into area A2. So, these two resistances can be viewed to be in parallel, just like shown here. Here in this diagram is shown as A by 2, because they have assumed both A1 and A2 to be half of A, but I am writing in a general form which is A1 and A2. If we just further analyze the resistances corresponding to F and G, then from there we can write T A minus T B will be equal to Q dot 1 into the resistance for F and Q dot 2 to resistance corresponding to G. So, that same temperature difference is active against them across them, but the heat transmission rate is different. Now, how to get an equivalent resistance for this particular layer? Just like in electrical circuit we do that, the same we can do in this case, that is this resistance is your R E, this is R H, this is R F and this is R G. So, first let us form an equivalent for this F and G part. So, this is your T1, resistance is R E, this is T2, resistance is R H, and so for our notation this is T A, this is T B, and this intermittent resistance is, let us say, R F G. Now, what will be R F G? We can get it by from here, or we can also use our electrical analogy. So, from there we can directly write that it will be equal to R F into R G by R F plus R G. Accordingly, the equivalent resistance for this entire circuit will be equal to R E plus this R F G plus R H, that is R E plus R F into R G by R F plus R G plus R H. So, this is be the equivalent resistance for this circuit where two resistances are connected in parallel. This way we can form heat transfer circuits, conduction heat transfer circuits for one dimensional steady state scenario following any kind of series and parallel configurations. So, I would like to stop here today. In the next class I shall be introducing you the concept of contact resistance, and then we shall be solving a few numerical problems to see the application of this conduction and convection resistances in case of Cartesian coordinate to demonstrate their application. So, to summarize our day, we have started with one dimensional heat transfer scenario, discussed the scope of that, starting from the generalized heat diffusion equation in all three coordinate direction. Then we continued with the Cartesian one and discuss the heat conduction in plane wall under 1D steady state condition. Then the concept of thermal resistance and the network of thermal resistances by connecting the resistances in series and parallel was discussed, and the overall heat transfer coefficient was also introduced. So, that is it for the day. In the next class, as I have mentioned, I shall be starting with these thermal resistances and their circuits, and I shall be solving a few numerical examples to demonstrate their use. Thank you very much.